Good morning, one and all. This is Dr. Diana. Welcome to session 19 on modern software engineering. We have been revising Unit 5 lately, which is on Agile development strategies. We have looked into what incremental requirements gathering is. We have looked into how a customer test can be conducted, and we have looked into the TDD life cycle, in which refactoring is a major role, and we have also used code smells to identify spots for refactoring. Once we identify certain spots for refactoring, the next is we have to change certain things in that might require a change in your design. So the next aspect we will be dealing with is the incremental design and architecture. Now, when we talk about incremental design, it is also called as evolutionary design. It allows you to build technical infrastructure incrementally in small pieces as you deliver your stories. Incremental design applies the concepts introduced in the test-driven development to all levels of design, right from planning, designing, development, and testing. Incremental design initially creates every design element such as method, class, namespace, or even architecture to solve a particular problem. Then you start adding to it incrementally. This incremental design and architecture helps you to deliver stories every week without compromising on the design quality. This incremental design applies the concepts introduced in the test-driven development to all levels of design. No matter what level of design you're looking at, the design tends to improve in bursts. Now you can correlate this idea with your code. Once you start developing your production code, you will always identify minor spots for refactoring. You keep on refactoring little by little. Then at some point of time, you will identify that you might have to take a major change with your production code. This is called as a burst. Typically, you will implement code into existing design for several cycles, taking minor changes as you go. Now, this will give you an idea for a major change. That is called as a breakthrough. Breakthroughs happen at all levels of design, right from methods to architecture. Now, this shows a time refactoring scale of how a breakthrough can be. So when you tabulate it across the value of your production code, when you start doing little bits of refactoring or minor refactoring every now and then across time, you see there are minor additions to the value of your code. But then some new idea or a new design hits you, and then you come up with a major change, or you incrementally design your very architecture. The value of your production code bursts very highly and then reaches a very high value. This is called as a breakthrough. Once you achieve your breakthrough, you can still add on using minor refactorings to help your code perform better. Now, at some point of time, when you try keeping refactoring things, you might be uncertain of what happens when you do some task with your production code. Say, for example, addition of a new feature may or may not work in your production code. To identify or to have a concrete answer of whether it will work or not, we are going to use spike solutions. A spike solution performs a small isolated experiment when you need more information on one particular aspect. It is a technical investigation specifically. This small experiment is used to research an answer to a particular problem. For example, a programmer might not know whether a Java throws an exception to arithmetic overflow. So the idea is to create a particular piece of code that creates a scenario of arithmetic overflow, and you then check whether Java is throwing an exception or not. This will give you a concrete answer when you are uncertain. The best way to implement a spike is usually to create a small program or a test that demonstrates the feature in question. These spike solutions clarify technical issues by setting aside the complexity of your production code. Even though you have 1,000 lines of code working in it, you just add 2 lines of code to check whether Java throws an arithmetic overflow exception or not. So you are independent of the complexity of your production code when you implement spike solutions. Sometimes you'll need to test an approach to your production code, or you may have to see how a design will probably work in your production code, or you can see how your persistence framework will work upon your production code. All these can be tested using spike solutions without having to actually develop them and then understand them. A spike solution is a learning technique based on performing small and concrete experiments. Some people perform these experiments in their production code, which can work well for small experiments, but as your code gets bigger, it can also increase the scope of possible error. Because of the 2 lines of code that you added right now for a spike solution, it can cause a lot of errors also. We should be very careful about that. Now, if these are scenarios where you can use your spike solutions. Something doesn't work as expected and you are not understanding why it doesn't. So is it because of the technology or because of your understanding? You can get an answer by implementing a spike solution. Then is it due to an unseen interaction with the production code and your test framework? You can check upon that. And you can also use standalone spikes to eliminate this sort of uncertainty and to derive concrete answers from your production code. Spike solutions for stories that you can estimate accurately. An alternative to scheduling a spike story is to provide a very high estimate. If you cannot do a spike story, you will have to come up with a very high estimate. Now these estimates are very risky because they might take longer than your estimated time, or in certain cases it may not be possible at all. So another option is to research problems by reading about the underlying theory and finding code snippets in books or online. So you can add a code snippet or get a code snippet from online forums and then try checking it as a spike. But the best way to really understand what's going on with your production code is to create your own spike. And once you have created all your spike stories and then you have understood exactly why is working, what and how, you now have understood your production code completely. But still, you have come up with a lot of refactoring, you achieved a major breakthrough, and you have achieved the best value for your production code possible from your end. But it may not perform as good as you expected. Why can it be? Or what are the reasons a performance fails? The first reason we all think of is the cache. The cache is one major role player in performance. So the next topic we will look into is the performance optimization. So when we talk about performance, we always link it with cache, and cache coherency requires that the data in the cache changes whenever the data in the underlying storage changes, and the vice versa. But it is very easy to get wrong in this place. It is not usually accomplished. So even if you have the best cache possible, your performance might still fail. So you can think of a scenario like this. You try reading a line of code from your file or a disk. It requires coordination from the CPU, the kernel, the virtual file system, the bus system, the hard drive controller, the hard drive cache, all the OS buffers, the system memory, and all the scheduling pipelines that run behind. So if your performance fails, it's not just the cache that causes the failure. You have a ton of other components that can cause that failure. All of these components exist to solve a particular problem, and each of them have certain ways by which they squeeze out your performance. So it is not possible to exhaustively test on what component has caused your performance to be lost. So an exhaustive methodology of identifying where your performance fails is impossible when you have so much of components. So you need to follow a holistic approach for such complex systems. This holistic approach uses a measure of the performance of the entire system. So you have a measure of your performance using some quantifiable numbers. Then you make some educated guess about what you can change in your system. You make a change in your system and then you remeasure your performance. If your performance gets better, you accommodate or keep the change with yourself, or else you discard this change. Now, an example for this is you take two applications. One is a very graphic intensive UI application. The other one is a Java program for billing. Now, both of their performance is very low. In that case, you add one RAM slot to your computer. The addition, you measure your performance without the RAM card, then you add your RAM card to it. Once you add your RAM card to it, you remeasure the performance of both applications. Now, for a graphic intensive application, the chances are high that an addition of a RAM card will improve the performance drastically. So if you see an improvement in your performance, accommodate your change or have the RAM card and start checking with other parameters. If addition of RAM card did not support increase in your performance, like in the form of a Java application which might not get any better because of a RAM slot, then you remove the RAM slot and then try checking with other components. So by this way you can add on to your particular system to check which exactly improves your performance. Once your performance test passes, then you can stop looking for opportunities. Then you can identify any missed spots of refactoring and then do a little bit of refactoring. You can run your test suite, integrate, and then again you will have to measure your performance. When you do this optimization has two major drawbacks. The first one is it leads to a very complex and buggy code. Your code becomes very complex when you try to optimize, and it also takes a lot of time before you deliver it to your customers. Both of these aspects, both the complex code and delivery time, lack in delivery time, are not of the customer's interest. So a customer doesn't like both of these. So when you try to optimize, you need to find a balance of what you optimize. Not everything requires optimization. You just have to identify certain spots which need a optimization that can be shown using a measurable value. So if you have a measurable value that indicates that you need an optimization there, only then optimize that spot. Otherwise, leave the spot untouched. And when we try to work with dedicated testers, they often act as technical investigators for the team. They may not work on the para-functional aspects. One of the ways they do this is to investigate non-functional requirements, also called as the para-functional requirements, such as the performance. Testers should help the customers articulate their non-functional requirements, and then they should be able to create and maintain test suites that evaluate the software's ability to meet these requirements. So apart from the test suites they create for testing the functional aspect of the system, they should also create test suites that help that test the performance and other aspects of the system. These test suites test the stability as well as the performance and the scalability of the architecture or your production code. So with this we complete our revision on performance optimization. Still we will be looking into one aspect from unit 5 which we will be revising in the next session, which is on explorative testing. For now, this is Dr. Diana signing off. Thank you.